Ever trying to make sense of something totally random? It's a trip, right? Today, we're diving into that world, how mathematicians wrangle random processes, especially those unpredictable paths they take, you know?
Yeah, it's like trying to predict, say, a butterfly's flight path, all that beauty and complexity, but with like a dash of chaos baked right in.
Love that analogy. And luckily, we've got a real expert to guide us. Deep dive time into this paper. Paths of stochastic processes, a sudden turnaround.
Catchy, huh? Sounds like a mouthful, but honestly, it's about a really intuitive way to get this whole randomness thing.
Okay, break it down for us. Paths in this context, what are we even talking about and why should we care?
Imagine you're tracking a stock price, up, down, all over that line. That's basically a path, how something changes randomly over time visually.
Yeah. So not just a single coin flip, more like the entire history of a thing that never sits still.
Exactly. And this goes way beyond stocks. A virus spreading, whether across a whole continent, even the temperature at like every spot on Earth, paths, tracing a journey through pure randomness.
Okay, now I see the challenge. We're putting order, like predictability, onto something that by definition is unpredictable.
The heart of the matter. For ages, the approach was define the whole random process first, then calculate each path's probability.
So figure out the odds of every single zig and zag a random thing could possibly do sounds ambitious.
Massively complex. Imagine needing probabilities for basically infinite variables. Like baking a cake with an infinitely long recipe, not going to happen.
Hence this sudden turnaround, right? The paper's got a different take.
Right on. Instead of starting with defining every single path, impossible as it is, this new way looks at the relationships between points in the process. This thing called the covariance function.
Okay, hold up. Covariance function, bit technical.
Picture this. 2 spots on a map. Covariance tells us how connected, say, temperatures are between them, measuring how interconnected the whole system is.
So not stuck on each path's details, we're looking bigger picture, how everything's influencing everything else.
You got it. And get this, from that covariance, that web of relationships, we can build the paths themselves, then the whole random field.
Talk about flipping the script. We're going backward, from connections to the actual events.
And this switch has perks. It's way more flexible. The old way made assumptions about randomness, like everything's a neat bell curve. Real world's messier than that. This new approach, we can model way more complex, realistic randomness.
So, truer picture of how randomness actually acts, no more simplifying it away, that's huge. But how do we make this covariance function? Well, math.
Time to grab our math toolkit. Don't worry, we'll keep it light. We start with something called a kernel. Basically the math version of the covariance function we're talking about.
So different kernels for different kinds of relationships, different randomness flavors?
You got it. Whole world of kernels out there. Matern kernels, for example, they're great at modeling, say, how temperature varies across a city.
So to understand how temperatures relate across, like, Chicago, we'd grab a Matern kernel.
Bingo. Each kernel, it's got its own quirks,
Yeah.
right? Suited for different random stuff we see.
This is where my brain usually checks out, but you're making it surprisingly clear. Now, each kernel has its own rules, its own little universe of what's possible. That's what Hilbert space, right? The math term.
Exactly. Think of the kernel like a recipe. The Hilbert space is all the awesome dishes you can make with it. Those dishes, those are all the possible paths, all the like well-behaved functions our chosen kernel allows.
So we've got kernels, Hilbert spaces, our math recipes for randomness, basically. But can we actually tell which path will happen, or is the universe always going to keep us guessing?
That's where this idea of smoothness comes in. How predictable a path is. It kind of depends on how smooth the kernel itself is, you know.
Smoothness, meaning like if we drew it on a graph, how smooth or jagged the line is.
Yeah, exactly. Some kernels, they give you paths that are pretty smooth, predictable. Others, they make paths that are all over the place, full of jumps and stuff.
Makes sense. Smoother kernel, probably a smoother, easier to predict path. But you mentioned this smoothness gap. That's where it gets really interesting, right?
Totally. Here's the kicker. Even with a perfectly smooth kernel, there's still a gap between how smooth we think the path should be and how smooth it actually is.
Hold on. Even with all this fancy math, our models and reality don't quite line up. Why is that?
It's that randomness at the heart of it all. Imagine drawing a perfectly straight line through a bunch of randomly scattered dots. You can try, but it'll always be a little wobbly, right?
So even if the overall pattern, the kernel, is smooth, the individual things it's describing, affected by randomness, can still be unpredictable.
Exactly. And this isn't just like a hunch. This paper, they've got this theorem 10 proving this whole smoothness gap thing mathematically.
Wait, there's a theorem that basically guarantees some level of unpredictability, even if the kernel's smooth.
That's the wild part. Theorem 10, it basically says, even if the kernel's telling us things should be perfectly smooth, totally predictable, the real paths, they'll always be a tad less smooth because randomness is just built into how things work.
That's kind of mind-blowing. It's like the universe has a built-in system to keep things interesting, to stop us from ever predicting everything perfectly.
Kind of humbling, right? We build these powerful models, but gotta accept we might never squash uncertainty entirely.
This turnaround, starting with the covariance instead of individual paths, it really changes how you think about approaching randomness altogether.
Totally. Encourages us to be cool with uncertainty and keep refining those models,
So we've covered paths, kernels, Hilbert spaces, all this cool math stuff. Even got a theorem reminding us the universe loves a good curveball. But what's it all mean, practically? Where do we go from here?
Well, this turnaround, it gives us a better, more accurate way to model random stuff, that's for sure. We can go beyond just assuming everything's a bell curve, deal with how messy the real world actually is.
No more forcing everything into that neat little bell curve box.
Exactly. And the smoothness gap, that inherent unpredictability, it's a good reminder. Even with our best models, perfect predictions are off the table.
And maybe that's a good thing, keeps things exciting, right?
Yeah.
But practically speaking, how does knowing about this gap change how we do things like, I don't know, financial predictions, weather forecasting, that kind of stuff?
Now you're talking. Gets to some real-world use for all this theoretical stuff.
Yeah.
Like those 7-day weather forecasts we all love to rely on.
Oh, don't even get me started. Lost count of how many picnics have been rained out despite a sunny forecast.
And that, my friend, is the smoothness gap in action. We've got crazy powerful weather models these days, tons of data, but those long-term forecasts still miss the mark sometimes, big time.
So not always that the models are bad, but more like proof of this unpredictability we've been talking about.
Exactly. Even with all our computing power, a smooth kernel suggesting some predictability, those tiny changes in air pressure, temperature, whatever, they can snowball into huge differences down the line, like the butterfly effect.
I love that analogy. So even with the best tools, there's a limit to how well we can predict the future, and that's fine.
More than fine. It's pretty awesome. Means we live in a world full of surprises where anything's possible.
Definitely keeps things interesting. But in a world obsessed with predictions, forecasts, all that, how do we square that desire for certainty with this smoothness gap reality? Do we just give up and accept the chaos?
Not at all. I think there's beauty in embracing that unpredictability. Keeps us humble, ready for anything, and always pushing our models further.
It's not about getting rid of uncertainty, but understanding it, working with it, acknowledging it's always there.
You got it. It's about realizing, even with all the knowledge in the world, we can't predict everything.
And maybe those limits are what make things interesting. Expect the unexpected, right? This deep dive's given me a whole new appreciation for that, and how math can help us understand even the most unpredictable parts of the universe.
Totally. And it shows something crucial. Just because something's hard to predict doesn't mean we can't understand it.
Great point. So, what other surprises might this journey have in store? What's next for exploring this world of randomness and the smoothness gap? It's crazy, right? The smoothness gap, something so like theoretical, actually changes how we see the whole world.
Shows how everything's connected for sure. You go deep into random processes, math equations and all, and it tells you how stuff works. Stock market, diseases spreading, even the weather we were just talking about.
Makes you realize uncertainty isn't something to be scared of,
It's just like
Yeah.
reality.
Yeah.
And understanding this smoothness gap thing, it can honestly help us make smarter choices, navigate the world knowing what's up.
So not about nailing perfect predictions, which we know is basically impossible now. It's more about knowing what we don't know and going from there.
Exactly. Factor that unpredictability into our models, our forecasts, even just everyday decisions,
Be ready for the curveballs.
Yeah.
And be cool with things maybe not going according to plan.
And that's where it gets exciting. Accepting that uncertainty, that surprise factor, can be kind of freeing, honestly.
Totally different way to look at things. Instead of freaking out about the unknown, we can be curious about it.
Exactly. Asking new questions, challenging what we think we know, always trying to understand this crazy world a little better.
This deep dive has given me a lot to think about, that's for sure. Who knew one paper about random processes and all that could spark so many ideas?
It's all about that curiosity, isn't it? and how elegant math is for making sense of the universe, our place in it, all that big stuff.
Couldn't have said it better myself. Well, on that note, think we've reached the end of our deep dive into paths of stochastic processes. A sudden turnaround. Quite a journey.
It's been a blast exploring all this with you.
The feeling's mutual. Huge thanks to our expert guest for, well, being our guide through this wild world of randomness and revelations, I guess you could call.
And to everyone listening, remember, uncertainty's not the enemy. Keep asking questions and never stop exploring.
Until next time, stay curious, folks.
Ever get a weather prediction totally wrong? Like, they're promising sunshine and you end up caught in a total downpour.
Yeah, it really reminds you that trying to predict the future, even something as random as the weather, is really complex.
Totally. And that takes us straight into today's deep dive. The world of stochastic processes. Basically, the math behind anything that involves randomness over time. And get this, we're looking at a research paper that's seriously shaking things up in this field. We're talking challenging some pretty fundamental assumptions about how we understand random paths.
And those random paths, they're everywhere, right? Tracking stock market chaos, figuring out how diseases spread, basically anything where we try to find patterns in randomness over time.
Okay, love it. So let's break this down. We've got excerpts from a paper, and the title alone is intriguing. Paths of Stochastic Processes, a Sudden Turnaround. So what's the traditional way we've defined these random paths, and where does it kind of fall apart?
Okay, so traditionally you'd start by defining the rules of this randomness, and we use something called a covariance function. Imagine, for example, trying to predict those temperature fluctuations we were talking about. The covariance function, what it does is it tells you how much the temperature at one point in time is related to the temperature at another point.
So like a relationship status for temperatures, but across time and space.
Exactly. But here's where it gets tricky. The next step is trying to define this thing called a joint probability distribution. And you need it for all the points in the process. And for things like temperature or stock prices, this is happening constantly over time. It's like trying to calculate the odds of every single point on an entire curve. It's essentially impossible.
Yeah, that sounds like a mathematical nightmare. So how have people even been working with this if it's fundamentally flawed?
Well, there's a pretty clever workaround, and it works for a specific type of stochastic process, Gaussian processes, those random processes that follow that bell curve distribution. These processes, they have some special properties that let us define the paths by kind of like cleverly looking at limits.
Limits. Okay, so like sneaking up on infinity without actually going there.
Exactly, you got it. This workaround, it's been the go-to method for a long time. But the thing is, it only works for these very specific Gaussian processes.
So this new research, this is offering a way to break free from that Gaussian mold.
Yeah.
Okay, now I'm intrigued. Tell me more about this turnaround approach.
Well, it kind of suggests this radical shift in perspective. Instead of starting with that whole random field and trying to wrangle these impossible probability distributions, they're saying, what if we start with the paths themselves and then define the random field?
Oh, okay, so completely flip the script. I like it. How do they even pull that off?
They use a technique called orthonormal expansion. Think of it like, how do I explain this? Imagine breaking down a really complex sound wave. And it's made up of all these simpler waves added together, right? So they're assigning random values to these simpler components. And by doing that, they can actually build up an entire path. And then from there, the complete random field.
Wow, so they're basically sidestepping that whole infinite probability distribution problem. That's pretty elegant. But what does it actually mean for the paths themselves? Like, what's different about the way they're being defined?
That's where things get really interesting. What they found is that the smoothness, how smooth or jagged a random path is, it's really closely tied to the properties of its covariance function.
Right, that covariance function, it's all about the relationships between those points.
Exactly. And remember those orthonormal expansions we talked about? The coefficients, the numbers we use in those expansions, those actually determine how smooth or bumpy the path ends up being.
So changing those coefficients is like changing the texture of the path itself. I'm picturing like a smooth line suddenly turning into a mountain range.
That's a great visualization. And here's the really wild part. Paths that are generated with this turnaround method, they can have totally different smoothness than those generated the traditional way. Even if they have the exact same covariance function, They've actually given this difference a name. They call it the smoothness gap.
So paths created with this new method,
Yeah.
they might be bumpier than we'd expect. Why does that even matter? What are the implications of this?
Well, because this bumpiness, it's reflecting a different kind of randomness than what we're used to seeing with that traditional approach. And that has some pretty major implications for how we model and understand random phenomena in the real world. Think about it this way. Imagine trying to model how a stock price changes over time.
Okay, yeah,
Got it.
a classic random path example.
Exactly. And traditional models, especially those that rely on those Gaussian processes, they might assume things are going to be pretty smooth. But we know markets can be way more volatile than that.
Yeah, tell me about it. I've seen my portfolio take a nosedive that would make anyone sweat.
Exactly. And those sudden drops, those unexpected jumps, that's where the smoothness gap becomes really important. That turnaround approach, because it allows for those bumpier paths, it might actually give us a much more realistic picture of how markets actually behave.
So instead of just looking at those smooth averages and trends, we're actually accounting for those wild swings that can happen out of nowhere.
Exactly. And this has huge implications, not just for understanding stock prices, but for any field where randomness is a factor.
So we're talking everything from predicting earthquakes to understanding how a virus spreads.
You got it.
Yeah.
Let's take climate change, for example. Traditional climate models, they're powerful, but they often struggle to accurately predict those extreme weather events, how frequent they are, how intense they are. They might show a gradual increase in those average temperatures, but they don't always capture those sudden heat waves or those crazy downpours that we're seeing more and more of these days.
Yeah, and those are often the most impactful, the most devastating consequences of a changing climate.
Precisely. Now imagine using this turnaround approach and building climate models that actually incorporate those bumpier paths, those sudden shifts. It could completely revolutionize our understanding of how the climate is changing and help us better prepare for what's to come.
It's like we're upgrading from a standard definition TV to a high definition one. Suddenly we're seeing details and nuances that were completely invisible before.
I like that analogy. And it's not just about seeing those details, it's about understanding what's happening at a deeper level. Why are these paths bumpier than we thought? What does that tell us about how these random processes really work?
It's like we've stumbled upon this hidden layer of complexity in how we perceive randomness.
And that's what I find so exciting about this research. This isn't just some mathematical curiosity. This is a fundamental shift in how we think that could have a huge impact on so many fields. It shows how important it is to always be questioning our assumptions, even in areas where we thought we had it all figured out.
Because sometimes those bumps in the road are more than just bumps. They're like signposts pointing us towards a deeper truth about the world.
Couldn't have said it better myself. It makes you wonder what other truths are out there just waiting for us to discover them, just by shifting our perspective, by embracing those bumpy paths.
This whole smoothness gap thing is really making me rethink how I see randomness. It's not just about things being unpredictable. It's about the specific nature of that unpredictability.
Exactly. And the tools we use to model that unpredictability, those have to evolve too.
Speaking of tools, you mentioned earlier that the traditional approach relies on those Gaussian processes. Can you maybe unpack that a little bit? What are they, and why is this new approach such a big deal for moving beyond them?
Sure, Gaussian processes, they're super useful in statistics and probability theory. They have this really elegant property where if you know how the process behaves at 2 points, you can basically extrapolate its behavior everywhere else. It's like having a magic wand that fills in all the gaps.
Sounds pretty convenient.
It is, but it relies on one very important assumption, that the random variables follow a normal distribution. You know that classic bell curve we see in statistics?
Okay, yeah, that classic bell curve shape.
Exactly. And for lots of phenomena, that assumption works great. But for others, it just doesn't accurately reflect what's happening.
Like those sudden market crashes we talked about. Those don't exactly fit that neat bell curve shape.
Exactly. And that's where this turnaround approach really shines. By shifting the focus from random fields to the paths themselves, it frees us from needing everything to fit that Gaussian constraint.
So we're not shackled to that bell curve anymore. That's huge.
It is. It opens up so many new possibilities for modeling those random phenomena that don't fit that neat Gaussian mold.
So we're talking about a more flexible, a more versatile way of understanding and predicting randomness. But with all this newfound freedom, how do we even know which approach is the right one for a specific problem?
That's the million-dollar question. And unfortunately, there's no one-size-fits-all answer.
No magic formula. My hopes are dashed.
I'm afraid not. But that's part of what makes this field so fascinating. It's this constant back and forth between mathematical rigor and real-world application. We need to really think about the specifics of the problem, the type of data we're working with. What are we actually trying to achieve?
So it's about asking the right questions just as much as finding the right answers.
Absolutely. And sometimes asking those questions leads us down some really unexpected paths. We uncover hidden connections and find ourselves challenging those long-held assumptions.
Just like this whole turnaround approach has challenged our assumptions about random paths.
Exactly. It's a powerful reminder that there's always more to learn. There are always new ways of looking at those old problems.
It's like we're on the verge of this whole new era of understanding randomness, this turnaround approach. It's like getting a new lens for our statistical telescopes.
Yeah.
It really is. And like any powerful tool, it comes with a learning curve.
Right.
There are so many questions to explore. How do we know how much bumpiness is the right amount for a model? How do we even interpret the results we get through this new lens?
Right. It's like we've been handed the keys to a brand new lab and
Yeah.
we get to design all these fascinating experiments. But speaking of experiments, what about those practical implications? We've talked about climate modeling, finance, so many areas. Can you walk me through a specific example of how this smoothness gap might actually play out in the real world?
Okay, let's go back to climate change for a second. Imagine you're trying to model the path of a hurricane. Traditional models, they might assume it's going to be a relatively smooth path based on all the historical data, atmospheric conditions, all that. But we know hurricanes can be unpredictable, right? They suddenly shift course, get way more intense really quickly, or even just stall out in the middle of nowhere.
Yeah, and those deviations from what's expected, those can have huge consequences for anyone in its path.
Exactly. And that's where that smoothness gap is so crucial. By being able to include those bumpier paths, those sudden deviations, we could potentially create hurricane models that are much more sensitive to just how unpredictable these storms can be.
So instead of just saying, okay, there's a chance it might go this way, we're saying, here are all the ways that unpredictable behavior could actually happen, and here's how likely each scenario is.
Yeah, that's a great way to put it. And having those more, nuanced probabilities, that could be so important for things like disaster preparedness, evacuation plans, even how insurance companies assess risk.
It's amazing to me how a small shift in our mathematical thinking can have these really tangible, real-world implications. It just shows how important it is to keep challenging those assumptions, always be on the lookout for new perspectives.
I couldn't agree more. It makes you think about what other breakthroughs are out there, just waiting for us to find them. All because we dared to question those smooth models we were using, to see those bumps in the road as potential clues.
It's like that old saying, the map is not the territory.
All right.
We have to be willing to redraw those maps as we explore, acknowledge those bumps, those detours. Those are the things that make the journey interesting.
And those bumps, they might just lead us to something totally new, discoveries we couldn't have even dreamed of.
Well said. This deep dive has been a real eye-opener. We've gone deep into the world of stochastic processes we've seen where the traditional approaches kind of break down and explored this groundbreaking new perspective with the turnaround method. It's really amazing to see how human ingenuity just keeps pushing the boundaries of what we know, even in a field as, seemingly abstract as mathematics.
It's been a pleasure exploring this with you. And to everyone listening, we hope this deep dive has sparked your own curiosity about just how complex randomness can be and the importance of always looking for new perspectives.
And as always, keep those minds open, keep exploring. Welcome to the Deep Dive. Today we're diving into the fascinating world of stochastic processes.
Oh, yeah.
Those mathematical models
Yeah.
that underpin so much of what we see around us.
Yeah.
Everything from predicting the weather
Wow.
to the stock market.
Absolutely.
And what we're interested in today is how we study the paths of these processes.
Yeah.
Those snapshots frozen in time.
Yeah. Those moments in time.
And get this, there's a really surprisingly elegant new approach
Yeah.
that's called a turnaround.
Yeah, it's fascinating. It really
Yeah.
flips the script on how we traditionally thought about these.
Okay.
To really appreciate this new approach, though,
Yeah.
let's take a quick look at how mathematicians have tackled this problem in the past.
Okay, let's unpack that traditional approach.
Okay.
So imagine like a map of temperatures across a country.
Okay.
That's our random field.
Right, a spatial representation.
The old school method starts by trying to define
Yeah.
how those temperatures at different points on the map are related to each other.
Okay.
And that relationship, my friend, is what we call the covariance function.
The covariance function, yeah, it's basically a measure of how much two things.
Okay.
In this case, the temperatures at those two locations tend to change together.
Right.
So if you've got two cities that are close to each other and they tend to have very similar temperatures, their covariance would be quite high.
So it's like saying, show me the global pattern of how these points on the map all relate to each other.
Exactly.
Right.
It gives you that big picture view. And so naturally you'd think, hey, if I know this global pattern, this covariance function,
Right.
I can then figure out what those individual snapshots look like, what those temperature distributions look like at specific moments in time.
Yeah.
The paths.
The paths, right.
But here's where the traditional approach runs into a bit of a snag.
Okay.
It requires us to define what's called a joint probability distribution
Okay.
for infinitely many random variables,
Okay.
which, to put it simply, is a concept that's not very well defined in standard probability theory.
So it's almost like we're trying to fit an infinite number of puzzle pieces together.
Right.
But the puzzle itself keeps changing shape.
Exactly. It gets very complicated very quickly.
Yeah. So no wonder mathematicians needed to find like a different way to approach this.
Right. They had to get a bit clever, and for a long time, they relied on certain workarounds, especially when dealing with what are called Gaussian processes, which are a specific type of stochastic process that pop up all over the place.
Right.
So what they would do is they would essentially focus on a smaller, more manageable set of points. And then they would use some of the nice properties of Gaussian distributions to kind of extend that idea to the infinite case. So it was a bit of a workaround, but it seemed to work for a lot of cases.
So they found a way to make it work, but it sounds like this new turnaround is offering something even more, just more elegant, I think.
Yeah, I think elegant is a great way to put it.
Yeah.
And it gets around a lot of these tricky issues as well.
Okay, so let's dive into that then.
Let's do it.
So we've got this traditional approach, and it sounds like it really struggles to pin down those paths.
Yeah, it gets a bit messy.
Those snapshots in time.
Yeah.
It sounds like this turnaround method you mentioned is offering like a breath of fresh air.
Yeah, it's a really cool, it's a really cool new way of looking at things.
So what's the big idea here?
So instead of going from the random field to that covariance function, and then trying to like wrestle those paths out of it, the turnaround just flips the script. It starts with the covariance function, that big picture view of how things are related. And it uses that to directly define the paths.
So instead of trying to like build up to the whole picture of these like tiny little pieces, we're saying we've got the whole picture.
We've got the framework.
Let's see what these little snapshots look like within this.
Yeah, let's see how those individual instances play out within that bigger context.
Got it.
And the really cool thing is this approach completely bypasses the need for that infinite joint probability distribution.
That we couldn't define.
Yeah. So it's a much more elegant solution in a lot of ways.
Elegant and efficient.
Yeah.
I like it.
And intuitively, it kind of makes sense, right?
It does.
Like we observe the world, we see these large-scale patterns, and then within those patterns, we see these individual instances playing out.
Right. So like if you think about like a hurricane, for example.
Exactly.
We know the general patterns that hurricanes follow. Right.
But each hurricane is its own.
Each one is unique. It's got its own path.
It's got its own little quirks.
Exactly.
Okay, so I'm with you so far.
Yeah.
But how does it actually work?
Okay, so the magic ingredient is something called orthonormal expansions.
Orthonormal expansions? Okay.
So think of it like this.
Okay.
Imagine you're building a house.
Okay.
You could start with like a giant pile of lumber.
Right.
And try to like carve out every single piece that you need.
Yeah.
Or you could use prefabricated walls and floors and roof sections.
Right.
That are all designed to fit together in a very specific way.
Okay, so you're saying these prefabricated sections are like our orthonormal functions.
Exactly.
Okay.
They're like pre-built components that we can use to construct our paths. Okay. Without having to start from scratch every time.
Exactly. You got it.
Okay.
So these orthonormal functions are basically like our Lego blocks.
I like it.
For building these paths.
Okay.
And the paper that you shared delves into two main types of these orthonormal expansions.
Okay.
Point-based expansions and Mercer expansions.
So two different ways to like construct our mathematical house here.
Exactly. Two different construction methods with their own pros and cons.
So what's the difference? What distinguishes these two? Okay, I'm with you so far. We've got our covariance blueprint, our orthonormal building blocks, and two different construction methods.
Yeah.
But this whole smoothness gap thing has really piqued my curiosity.
Okay.
So we're defining these paths, these snapshots in time.
Right.
based on the smooth covariance function.
Yeah.
Right.
Okay.
But are the paths themselves as smooth?
That's a great question, and that's where things get really interesting.
Okay.
So what they found is that there's this difference in smoothness
Right.
between those original functions
Right.
that the covariance represents
Okay.
and the paths that we actually end up generating using the turnaround.
So a smoothness gap.
Yeah, like a gap in smoothness.
So even though our starting point is smooth,
Yeah,
the paths might have a few bumps in them.
exactly.
Yeah.
It's not a perfect one-to-one mapping.
Okay.
Let me try and give you a visual.
Okay.
Imagine our covariance function, that global pattern, is like a perfectly smooth lake,
Okay.
right? Just glassy smooth.
Okay.
When we use the turnaround to generate those paths, those snapshots of the lake's surface at different points in time,
Okay.
they might look a little bit more like
what?
ripples or tiny waves disturbing that stillness.
So even though we've got the smooth blueprint and we're using our nice orthonormal building blocks,
Yeah.
the final result isn't quite as smooth.
Yeah, exactly.
Why is that?
Well, it all comes down to randomness.
Okay.
Remember we talked about those orthonormal expansions?
They go block.
Our prefabricated pieces, right?
Yeah.
We use random coefficients to actually combine those and create those paths.
Okay.
So it's kind of like if you had those pre-cut pieces of wood for your house,
Yeah.
but there was a little bit of variation in each piece.
Okay.
Maybe due to the wood grain or something.
Yes.
You can follow the blueprint as closely as you want. But those tiny variations are going to add some randomness to that final structure.
So this smoothness gap is almost like the character
Yeah, in a way.
that emerges from that randomness.
It's that little bit of uniqueness
Yeah.
that emerges from the randomness of the process.
Okay, so it's not really a flaw.
Right.
It's just a consequence of the way we're bringing those paths to life.
Exactly. It's just a natural consequence of the way we're constructing these things.
And it has implications, I imagine, for like
Oh, absolutely.
modeling and stuff like that.
Yeah, so like in financial modeling,
Right, yeah.
where stochastic processes are used to
Yeah, to like understand.
stock markets and things.
Right.
Being aware of that smoothness gap can actually lead to
What more?
more nuanced and potentially more accurate predictions.
Because you're not expecting things to be perfectly smooth.
Exactly.
Yeah.
You're allowing for that bit of randomness and that little bit of unpredictability.
Which honestly reflects the real world better anyway. Right?
Exactly.
Nothing's ever perfectly smooth.
The real world is messy.
Yeah.
And these stochastic processes help us to embrace that messiness.
It's like we're acknowledging that even with the most elegant model,
Right.
there's always that element
There's always that unpredictable
of
element.
predictability.
Yeah, and that's what makes it all so interesting.
It really does.
I mean, this has implications not just for finance, but any field that uses these processes.
We use them for everything.
Weather patterns,
Disease spread.
traffic flow.
Yeah.
Understanding that smoothness gap can really change how we approach these things.
Yeah.
And lead to more robust and accurate models.
So it sounds like this turnaround is more than just a new method.
It's a whole new perspective.
It's a whole new lens through which to view these processes.
Yeah, it's a really powerful way of thinking about these things.
That's really cool.
It's exciting stuff, and the best part is,
Yeah.
this is just the beginning.
Right.
There's so much more to explore.
Yeah, like how does this smoothness gap change for different types of processes?
Exactly, different types of processes, different applications.
What kind of computational tools can we develop now that we understand this?
Exactly. It's really opened up a whole new avenue of research.
Wow.
I think this deep dive has really just scratched the surface.
It really has. And on that note,
Yeah.
we'll leave you with this final thought.
Okay.
As you go about your day, take a moment to think about those subtle ways
Right.
that randomness shapes the world around you.
Yeah.
Whether it's the patterns of leaves falling from a tree
Yeah.
or the ebb and flow of traffic on your way to work.
Absolutely.
It's a beautiful and complex dance.
It really is.
And I think understanding it even just a little bit better
Yeah.
can give you a whole new level of appreciation for the intricacies of our universe.
I couldn't agree more.
So until next time,
Yes.
keep exploring, keep asking those questions,
Keep diving deep.
and keep diving deep.
Ever try picturing something as chaotic as like a global temperature map?
Oh, at any given moment.
Yeah, like every single point on Earth having a temperature.
And they're all connected and like constantly in flux. It's, wow, it's kind of mind-boggling.
How do you even begin to model that, right?
Yeah.
That's what we're diving into today, the wild world of stochastic processes.
Yes.
We're looking at how researchers are trying to find order in the randomness,
Yeah.
Things like weather patterns, stock prices, all that.
It's like trying to bottle the unpredictable or something.
Exactly.
Oh,
And this paper we're looking at today throws a real curveball into how we usually think about these processes.
okay.
Be prepared to have your assumptions challenged today.
I love a good challenge.
So let's start basic. We're dealing with randomness over time or space, right?
Yeah, yeah.
How do mathematicians even begin to grasp that?
Well, they use something called a random field.
Okay.
So imagine a field not of grass, but of, infinite points.
Okay.
Each one is like representing a possible value, like those temperature readings we talked about, all across the globe.
Okay.
Each point has like a random temperature, but importantly, they're all correlated, right?
So it's not just like picking random numbers out of a hat.
Right.
There's a
Exactly.
method to the madness.
Yeah.
But capturing that interconnected randomness, that just sounds near impossible.
Yeah, it's a mathematical puzzle for sure.
Yes.
And traditionally, there have been sort of two main approaches.
Okay.
One is to start by trying to define this massive random field, right?
Okay.
And then figure out how all the points within it relate to each other. And that involves something called a covariance function, which basically describes how much the value at one point influences the value at another.
So if we know the temperature in London, the covariance function will tell us what it's like in Paris.
Precisely.
Like a mathematical weather whisperer.
Exactly. But imagine trying to come up with a rule book for an infinite number of points,
Right.
all influencing each other. It gets very complex very quickly.
No kidding. So what's the other approach? Do they just throw their hands up and say randomness wins?
Not quite. Another common method is to focus on something called Gaussian processes,
Okay.
which are kind of like statistical shortcuts, if you will,
Okay.
that let mathematicians work with these like really complex relationships a little more easily.
I've heard that term thrown around, Gaussian processes. They're kind of a big deal, right?
They are. And they work by zeroing in on that covariance function we talked about.
Okay.
The beauty is, with a Gaussian process, you only need to define the covariance, and boom, you can describe the relationship between any 2 points.
Sounds like a pretty sweet deal.
Yeah.
But you mentioned a curveball. Does this paper say Gaussian processes are out?
No.
Back to the drawing board.
Not exactly. It's more like they're tackling a fundamental issue that both of these traditional methods kind of dance around,
Okay.
which is the very definition of a path in a stochastic process.
Okay, so now we're getting to the heart of the matter. What do they mean by paths?
Okay, so imagine you're tracking a single data point over time or space.
Okay.
Let's stick with our temperature example, right?
Yeah.
Imagine following the temperature in London over a week. That sequence of temperatures, that's a path.
Okay, so it's like a journey through the random field,
Exactly.
but you're focusing on the ups and downs of just one point.
Exactly. And here's where this new research really kind of shakes things up.
Okay.
Instead of starting with that random field, that massive field,
Right.
and then trying to make sense of the paths within it, they're flipping the script.
Okay.
They're starting with the covariance function itself.
So they're saying, hold on, let's not get ahead of ourselves with this massive field.
Yeah.
Let's focus on the connections,
Exactly.
the paths, and see what happens.
They're basically saying, if we know how all the points are connected, we can actually build up that entire field from there.
Interesting.
And to do this, they use this concept called a kernel, which is kind of like a distilled version of the covariance function.
Okay.
It captures the relationship between points in a more compact, kind of elegant way.
Okay, so the kernel's like a concentrated formula for those connections,
You're right.
and they use that to build the paths.
Exactly.
But how do we get from these paths to the actual random field? I'm a little lost there.
So this is where it gets really fascinating. They use something called an orthonormal expansion.
Okay.
Think of it like a set of perfectly placed, perfectly sized Lego blocks
Okay.
that can be used to construct any point within our random field.
So it's like a framework
Yes,
that gives them a structure to build something meaningful from these random values.
precisely. They take these Lego blocks, each weighted by a randomly drawn number, and stack them together according to the blueprint provided by that kernel.
Okay.
And voila, you have your path, the sequence of values that perfectly reflects the relationships laid out by the covariance function.
Wow. So they're constructing a random walk, but instead of on a sidewalk, it's through this like abstract mathematical space
Yeah,
guided by the kernel.
that's a great way to put it. And because they've constructed these paths so meticulously, they can then define the random field as simply the collection of all possible values that those paths could take.
Wow. So they're essentially saying, forget the random field at first. Let's talk about the paths these random values can take.
Yes,
And from that, the field kind of magically emerges.
you got it. It's a radical new perspective on a classic problem. But it gets even more interesting. Remember how we talked about that covariance function defining the relationships between points?
Yeah.
Well, turns out this new way of looking at paths has led to a really surprising discovery about how smooth these random processes can actually be.
Okay, now I'm really hooked. Smoothness, what does that even mean in this context?
Yeah.
And what did they find? So we're talking about how smooth, like how much those random paths fluctuate.
Exactly. Imagine like a stock market graph.
Okay. Yeah.
A smooth path would have gentle rises and falls.
Okay.
A rough one, on the other hand, would be all over the place, spikes and dips everywhere.
I'm with you. So what's the big reveal with smoothness and this like paths first approach?
Well, this is where it gets really interesting. They found that even if you design a covariance function to create smooth transitions,
Okay.
the paths themselves, they can't help but be a little rough around the edges.
Wait, so even with this new method, we can't totally eliminate those like unexpected jumps and dips?
Yeah, there's a limit to how predictable those random values can be.
That's kind of unsettling, right? We're talking about math here. I feel like we should be able to control randomness if we set the rules carefully enough.
You'd think so, wouldn't you? But that's the fascinating part. It's like there's some fundamental limit to how much order we can impose on chaos,
Wow.
even in a carefully constructed mathematical world.
That's a pretty profound thought that we're talking about, like mathematical models reflecting something inherent about randomness itself.
Exactly. It's a bit humbling when you think about it.
Yeah.
But beyond just the head scratching, it also has some real world implications
Okay.
for how we model complex systems.
Okay, so let's bring it back down to earth then. What does this smoothness surprise, what does that actually mean for, like, our weather example?
Okay, so imagine you're a meteorologist
Okay.
trying to predict the weather a month out.
Okay.
You might use a model that assumes a certain level of smoothness, right?
Right. Because in the real world, it doesn't go from like 80 degrees and sunny to a blizzard the next day.
Exactly.
Mm.
But this research suggests that even the best models, right, built on those totally reasonable assumptions of smoothness, they'll still have a certain level of inherent roughness in their predictions.
So no matter how much data we gather or how powerful our computers get, there's always going to be a limit to how accurate like those long-term forecasts can be.
Precisely. And that might seem, a bit disheartening at first.
Yeah.
But there's also a certain beauty in acknowledging the limitations of our models. It encourages us to be more adaptable, more prepared for those unexpected events.
It's a good reminder we don't have it all figured out. This whole roughness thing, this unpredictability, it makes you wonder about other areas where we rely on models. Like, what about financial markets?
You've hit on a crucial point. Imagine trying to predict the stock market.
That's right.
People have been trying to do that forever.
Right.
Relying on all sorts of complex models.
And we've seen time and time again how those models can be like incredibly accurate one day and totally off the next.
Exactly. And this research suggests that some of that inherent unpredictability, might be baked into the very systems we're trying to model. It's not just a matter of not having enough data,
right,
or, sophisticated enough algorithms. It's about recognizing there might be fundamental limits to how predictable these systems can even be.
That's kind of a game changer. So are you saying we should just give up on trying to improve our models, just embrace the chaos?
Not at all. It's about approaching these problems with a healthy dose of humility. We can and should continue to refine our models, gather more data, strive for better predictions.
But also accept that there will always be that element of the unknown, that little bit of roughness that we can't quite smooth out. Yeah.
Exactly. And who knows, perhaps that acknowledgement will lead to entirely new approaches, new ways of thinking about risk and prediction.
It's like that quote, the more you know, the more you realize you know nothing.
I love that. It really speaks to the heart of scientific inquiry.
Right.
Every answer just opens up a dozen new questions.
Right.
And that's what makes this research so exciting.
It's not just about like the specific findings on stochastic processes, but these larger questions it raises about how we approach complex systems in general.
Absolutely. And there's another aspect to this paper that I think is worth highlighting.
Okay.
The way it challenges us to rethink how we even define and study paths in the first place.
Oh, we haven't really touched on that yet. How do they want us to rethink paths?
Well, traditionally, we've often focused on like specific points along a path,
Okay.
like asking, what's the probability the stock will hit, like, $100 a share next week?
Yeah, looking at these like snapshots in time.
Precisely. But this paper, by starting with the connections,
Yeah.
it encourages us to take a more like holistic view,
Okay.
to appreciate the entire journey, not just like the individual stops along the way.
I like the sound of that. Focus on the whole story, not just those isolated data points. But how do we actually apply that thinking?
It's about shifting our perspective from isolated events to patterns over time. For example, instead of asking, will a hurricane hit this particular coastline this year,
Hmm.
we might ask, how often can we expect hurricanes of a certain intensity to make landfall over the next decade?
So instead of trying to predict individual coin flips, we're looking at like the overall distribution of heads and tails over 1,000 flips.
Exactly. It's a subtle shift, but it can fundamentally change how we analyze and interpret data,
Hmm.
especially when dealing with these like complex interconnected systems.
This is definitely making me rethink how I approach these kinds of problems. It's like zooming out and seeing the bigger picture, rather than getting caught up in all the little details.
Yeah.
But I have to ask, are there any downsides to this whole paths first approach? It seems like there are always trade-offs with new approaches, new challenges pop up. What are we giving up for this like broader perspective?
That's a great question. And while this path-first approach, it is elegant,
Yeah.
it's still, it's relatively new.
Okay.
The traditional methods we talked about, they might have limitations, but
Yeah.
they have well-established tools, techniques.
So we're talking about a little bit of uncharted territory here. We're going to have to build new maps for this new landscape.
Precisely. To really unlock the potential of this path-first perspective, we need new algorithms,
Okay.
new computational methods, ones that can really handle these types of models effectively.
So it's like a call to action to all the mathematicians out there.
It certainly is. It'll be really exciting to see what new tools and insights emerge as more researchers kind of dig into this approach.
This whole conversation makes me think about that whole philosophical debate about like fate versus free will.
Oh, interesting.
If even our mathematical models can't escape this inherent roughness, does that tell us something fundamental about how the universe works?
Now you're really diving into the deep end. It's these intersections between like science and philosophy that I find so fascinating. This paper doesn't give us all the answers, but it definitely gives us a new way to think about those big questions.
It's like that saying, the more you learn, the more you realize how much you don't know.
Exactly. It's not about finding all the answers, but
Yeah.
about constantly refining the questions, right?
Yeah.
And maybe this inherent roughness, this unpredictability, isn't something to be like afraid of, but something to embrace.
Yeah, without a little chaos, life would be pretty boring.
Exactly.
Yeah.
It's that element of surprise, that hint of the unknown that keeps things interesting in the world and in our quest to understand it all.
I think that's the perfect place to wrap up our deep dive for today. We've explored the wild world of stochastic processes, turned traditional models on their head, and maybe uncovered a surprising truth. Even in math, there's beauty in a little roughness.
It's been a pleasure exploring these ideas with you.
And for our listeners, we'll leave you with this. If you had to redesign our simulations, knowing that perfect smoothness is basically impossible, how would you approach modeling the complex systems that make up our world? Until next time, keep asking those big questions and embracing the beauty of the unknown. All right, so get this. Imagine like trying to predict something as wild and random as, I don't know, the stock market.
Yeah.
We've got all these complex systems out there where randomness like plays this huge role,
Right.
but it turns out the way we've been looking at it might be, well, a little off.
Yeah.
So today we're diving into this paper and it's called, get this, Paths of Stochastic Processes, a Sudden Turnaround.
Okay.
And let me tell you, it lives up to the name.
It's pretty mind-blowing.
Yeah.
Even for someone like me who's been knee-deep in stochastic processes for years.
Right.
This paper really throws the traditional rulebook out the window.
Okay, so for our listeners who maybe aren't fluent in like stochastic lingo,
Sure.
let's break it down a little bit. We're talking about paths, which is really just like a fancy way of saying
Right.
how randomness plays out over time.
Exactly.
Right.
Yeah, think of it like tracking the path of a hurricane.
Okay.
It's unpredictable.
Right.
It zigs and zags, but there's a method to the madness.
Right.
So traditionally, we've tried to understand these paths by starting with the whole chaotic system
Okay.
and then kind of zooming in.
That makes sense. Right.
Yeah.
Get a sense of the big picture.
Mhm.
And then, but that's where things get tricky.
Exactly. Imagine trying to predict that hurricane's path by analyzing the movement of every single air molecule that's involved.
Oh, wow.
It's overwhelming.
Yeah.
And when you're dealing with potentially infinitely many random variables,
Right.
like trying to map the temperature at every point on Earth simultaneously,
Wow.
the old approach just hits a wall.
So we've been trying to navigate through a hurricane with a microscope instead of a weather map.
Essentially, yeah.
Yeah.
And that's the genius of this new paper. It's
Right.
like, what if we start with the map instead?
Okay.
So instead of getting bogged down in these infinite details,
Yeah.
it starts with a global view
Okay.
of the relationships between all those random variables.
Okay.
And this is something called the covariance function.
Okay, hold on, because I can already feel my brain starting to sweat a little bit.
Sure.
Covariance function.
Yeah.
That's our new starting point.
It is, yeah. Think of it like the DNA
Okay.
of the randomness we're looking at. It's a function that tells us how different parts of the system are related to each other.
Okay.
It gives us a sense of the overall pattern.
So if we're trying to understand, I don't know, the stock market,
Yeah.
instead of looking at every single trade, we're looking for the underlying relationships that drive the market's ups and downs.
You got it.
Okay.
And from this covariance DNA, this
Yeah.
new approach lets us define those paths of randomness
Okay.
in a surprisingly elegant way.
Elegant. Math and elegance aren't usually two words I use in the same sentence.
Oh, trust me. This is where it gets really cool.
Okay.
To work with this covariance function,
Mm-hmm.
we have to step into a special mathematical space
Okay.
called a Hilbert space.
Hilbert space.
Yeah.
Hilbert space sounds intimidating. Yeah.
But I'm guessing it's not as scary as it sounds?
Not at all.
Okay.
Think of it like a giant library.
Okay.
But instead of books,
Yeah.
it's filled with functions.
Right.
So it's these mathematical recipes that describe different types of patterns.
Okay.
And each Hilbert space is kind of custom built based on that covariance function we talked about.
Okay.
So it's kind of like how a library might have
Right.
different sections for,
Uh-huh.
mystery or sci-fi or romance.
Right. Okay, so we've got our covariance DNA.
Yeah.
We're in this special library.
Right.
What kind of books are we pulling off the shelves here?
That's where the real magic happens.
Okay.
You start using these special tools called orthonormal expansions.
Okay.
And,
Don't worry, you don't need to memorize that name.
okay, good.
Basically, these are like the building blocks within that Hilbert space.
Okay.
Carefully chosen functions that we can combine to create any path we want.
Wow.
It's like having a set of Legos.
Right.
They can build any structure imaginable.
Okay.
But instead of castles, we're building paths of randomness.
Okay, so we're talking about creating custom paths to match any random scenario.
Exactly.
Why is this such a big deal?
Because it completely changes the game.
Okay.
Remember how that old approach struggled with infinite variables?
Yeah, yeah.
Well, this new method,
Yeah.
it bypasses that problem completely.
Oh, wow.
We no longer need to define every single point on the path.
Right.
We can let the covariance function and the Hilbert space do the heavy lifting.
Okay.
And the really cool part is
Yeah.
this approach lines up perfectly with something you might have heard of, Gaussian processes.
Gaussian processes, yeah, ringing a bell. But remind me why those are so important.
They're like the bread and butter of statistics and machine learning.
Right. Okay.
Gaussian processes are used everywhere, from predicting, stock prices to modeling weather patterns.
Right.
And this new approach actually makes many of the existing arguments about Gaussian processes much simpler
Okay.
and much more intuitive.
So not only does it solve this huge problem,
Yeah.
but it also makes the stuff we already use even better.
Exactly.
I'm starting to see why you called it a sudden turnaround.
And here's the best part.
Okay.
It's not limited to just Gaussian processes.
Okay.
This new way of defining paths,
It opens up a whole new universe of possibilities
Right.
for working with other types of randomness.
okay.
Stuff that doesn't fit neatly into those familiar bell curves.
Like what? Give me an example.
Think about like stock market crashes.
Okay.
Those sudden dramatic plunges.
Right.
They aren't exactly following a nice predictable pattern.
Right.
They're more like rogue waves.
Okay.
And traditional models, which often, rely on Gaussian assumptions,
Right.
they struggle to capture that kind of, extreme chaotic behavior.
So this new approach could help us, like, predict those, what do you call them, those black swan events?
Yeah, exactly.
Things that, like,
Right.
seem to come out of nowhere, but
Mhm.
can have these, like, huge consequences. Exactly. By using this more flexible framework,
Right.
we can start to get a handle on those wild, non-Gaussian events that make the world so unpredictable.
Okay.
So we're not just limited to the smooth, predictable stuff anymore.
Right.
We can finally start to tackle that messy reality head on.
This is blowing my mind. We're going from like
Yeah.
neatly trimmed hedges to like
Right.
exploring the untamed wilderness of randomness.
Exactly.
But hold on, you mentioned earlier something about smoothness.
Yeah.
That this new approach reveals something unexpected about how smooth or chaotic these paths actually are.
Ah, yes, the smoothness gap.
Okay.
This is where things get really interesting,
Okay.
even a bit philosophical.
Okay.
You see, the covariance function, our DNA of randomness,
Yeah. Okay.
it gives us a sense of how smooth we might expect the path to be.
Okay.
But what this new approach reveals is that the actual realized path, the one that plays out in the real world,
Okay.
can be surprisingly different.
Different how?
Yeah.
Give me an analogy, because I'm feeling like I'm like wandering through a hall of mirrors here.
Imagine you're looking at a map of a mountain range.
Okay.
The contours on the map might suggest a fairly gradual incline,
Okay.
nice and smooth.
Right.
But when you actually start hiking, you realize the terrain is much rougher than you expected,
Okay.
with hidden crevasses and jagged peaks.
So the map or covariance function doesn't tell the whole story.
Exactly. There's a gap between the expected smoothness based on the map
Right.
and the actual realized roughness of the terrain.
Okay.
And that gap is all thanks to the inherent randomness
Right.
of the process itself.
So even with our fancy covariance map,
Yeah.
we can't escape those like surprise detours that randomness throws our way.
Yeah,
It's like humbling and a little terrifying at the same time.
it is. But here's the thing.
Okay.
By understanding this smoothness gap,
Right.
we can actually develop, better tools,
Okay.
smarter algorithms
Right.
that can handle that real world roughness.
Okay.
So we're not just,
Yeah.
trying to smooth over the bumps anymore.
Right.
We're embracing the complexity.
It's like we're upgrading from those like old paper maps to
Yes.
high-tech GPS
Exactly.
that knows about all the like
Right.
the back roads and hidden trails and stuff.
Precisely. And this has huge implications for all sorts of fields.
Okay.
Imagine being able to create, more accurate financial models
Right.
that can, like, anticipate those market crashes.
Right.
Or developing climate models.
Okay.
That can better account for the unpredictable fluctuations of our planet.
We're talking about a whole new like level of understanding, a way to see the
Right.
patterns within the chaos
Yeah, exactly.
that we might have missed before.
It all stems from this fundamental shift
Yeah.
in how we view paths
Okay.
from these infinitely complex objects
Right.
to something we can actually grasp and manipulate and learn from.
Right.
It's a whole new lens
Okay.
through which to view the world.
It's like it's like we've been handed the keys to like a secret laboratory.
Yeah.
And now like we get to experiment and see what amazing discoveries we can make.
And who knows what we might find, right?
Yeah.
I mean, this new understanding of paths, it has the potential to revolutionize how we approach everything from artificial intelligence to like quantum physics.
Wow.
We're just scratching the surface of what's possible.
It's incredible to think that something as like seemingly abstract as defining paths could have such a like profound impact on our understanding of the universe.
Yeah. That's the beauty of mathematics and science, isn't it?
Yeah.
It's about constantly questioning and pushing the boundaries.
Right.
And discovering those hidden connections that tie everything together.
Well, I think it's safe to say that this deep dive into stochastic processes has left us with more questions than answers,
Yeah,
but in the best way possible.
I agree.
So
Yeah.
if you're as intrigued by this sudden turnaround in understanding paths as we are,
Yes,
we encourage you to check out the original research paper.
please do.
We'll have a link for you in the show notes.
Happy exploring.
And until next time.
Keep asking questions.
Mm-hmm.
Keep diving deep.
Right. And most importantly, keep that curiosity alive.